I can give me some.
We're going to get started then. All right. So it feels like the lights are not all on in this room. Are they on? All at once. Ready? 1, 2, 3. The clapper's not working. Hi guys. Okay. So I debated. My turn. I debated what to talk about today, and I'm going to give you the quick rundown. The topic that would have naturally come in the progression was the derivation of the Schwarzschild solution to Einstein's equation, which is the solution that we're going to spend a lot of time studying and discovering interesting properties of. But it's a pretty dry lecture, to be quite honest. It's like just solving a differential equation, or a set of differential equations. The next topic, though, is actually taking the Schwarzschild solution and exploring its properties, which leads us to some of the ways that we actually test and verify general relativity. I didn't want to leave you with a bad taste in your mouth as you go to frolic in the sun for spring break, so I decided to swap the order. So what I'm going to start with today is simply giving you the Schwarzschild solution, and then we'll explore its properties, and then when we come back from spring break, we'll actually see that it is in fact a solution and derive it. And that there's some very important features of the Schwarzschild solution which, unless you see it derived, you might question whether it makes sense. Because it's going to lead us invariably to black holes, okay? And we're going to use it to describe black holes. So if you're going to accept that black holes are a reality, you really need to have confidence in this particular solution. So we will do that after spring break, but for now we're just going to explore its features. Okay, so as always, recall that GR has 2 parts. Okay, part number 1, Einstein's equation tells us what? Let me get a victim. Colton. Where are you, Colton? There you are, Colton. Yeah. What does Einstein's equation tell us? It tells us how blank does blank.
How spaces get curved.
Right, basically. Einstein's equation tells us how sources curve space time. Okay. And does anybody want to tell me the second half of GR? Say it again?
Geodesic.
So the geodesic equation is part of it, but we actually extended it a little bit to the minimal coupling. So the minimal coupling, remember, is just this idea that anytime you see a metric, you replace it with a curved metric. Anytime you see a derivative, you replace it with the covariant derivative. But the minimal coupling can tell us how pretty much any physics on flat space changes when you go to curved space, including the motion of free particles, which leads to the geodesic equation. Okay, so for our first non-trivial geometry, let me just write down what our metric is going to be. So we've investigated, obviously, Minkowski space in 4 dimensions, whose line element is minus dc squared plus dx squared plus dy squared plus dz squared. This is when, of course, you're using rectangular coordinates. Okay. When we solve for the Schwarzschild geometry, our assumption is going to be a spherical geometry.
Is that okay then?
You got candles?
What?
You got candles?
No, I just couldn't see the board. I'll bring candles next time.
Okay, bring candles next time. Anyway, so this is obviously the flat space geometry that we've seen, and it's the flat space geometry that's relevant for special relativity. But when we look at the Schwarzschild geometry, really the only assumption that we're going to make, and this is the surprising feature because we get a lot of mileage out of just one assumption, the only assumption we're going to make is spherical symmetry. That, of course, is a very safe assumption for applying general relativity to astrophysical phenomena because most large astrophysical objects are approximately spheres, so planets, stars, and so forth. Of course, that situation will change when we try and apply GR to the entire universe, which we'll do at the end. That's cosmology. But when we apply GR to the to a localized source, then assuming spherical symmetry leads us to the Schwarzschild geometry, which uses, probably not surprisingly, the analog of spherical polar coordinates. So you have a radial direction, a theta direction, and a phi direction. Although I want to be a little bit careful, these are actually what are called Schwarzschild coordinates. They aren't directly spherical polar coordinates, and you'll understand that distinction when we actually derive the solution. But in these coordinates, the metric ds squared, or the line element, takes the following form: 1 minus 2 capital G m, where m is a mass, over r, dt squared, plus 1 minus 2 gm over r to the minus 1, dr squared, plus r squared d omega squared, where d omega squared can be blown up into the usual term d theta squared plus sine squared theta d phi squared. Okay, so that last little bit, the r squared d omega squared, just looks like the angular part of flat space if you go to spherical polar coordinates. Yep.
So is this still considered Minkowski's?
No, this is not, okay. So if you put this, if you calculate the Riemann curvature tensor for this space, it will be non-zero.
Oh.
It is not a flat space. So I am not taking this and just writing it in spherical polar coordinates. We don't need a whole lecture to do that. I could do that in about 3 minutes. This is a different solution to Einstein's equations. And again, we will derive this the Tuesday after spring break. But for now, it's going to be a given. Of course, we can take the line element and we can write the metric in a matrix form just by peeling off the various terms. And then you have zeros everywhere else. Okay. Now, okay, so what I am going to be aiming to do today is to take this space as given. So we're not really going to mess around with part 1 today. We're just going to say we have a curved space, right? And what we're going to do is we're going to spend our time kind of using the second part to explore properties of this space, but in particular, we would like to explore properties of this space in contrast with good old Newtonian gravity. Okay? Because what we want to do is we want to see what new and different things does general relativity give us. Because I should say, if the only new thing that general relativity gave us was this interpretation of gravity as the curvature of space-time, if there was no like measurable, detectable difference, who cares about the interpretation? Like it's the same thing as Newtonian gravity. But we will discover that there are explicit predictions of general relativity which are different from Newtonian gravity, and that of course allows you to go out and test and see which one's actually correct. Okay? So I'm going to be contrasting this with what we do in Newtonian gravity, and therefore we should start with a review of Newtonian gravity. Now this review is going to be not at the physics 1 level. It is hopefully going to be at the IMEC level, the intermediate mechanics level, and so I hope that what I'm about to do is review for most of you if you took IMEC. If not, we can all call up Dr. Callan and have a conversation with him. So we are interested in talking about central forces in good old Newtonian mechanics. Okay? So first of all, when we say a central force, what we have in mind is that the force vectors, first of all, only have an r component. There's no component to the vectors in the theta or the phi directions. And furthermore, their R component only depends on R. So things only point in R and they only depend on R. Now you're familiar with the fact that these gravitational forces in the Newtonian case depend on R. The further away you get, the smaller the gravitational force, so it varies as 1 over R squared. But I'm just going to say some things about general central forces, and then we'll eventually come to the specific case of gravity. So for a central force, one of the first conclusions that you can reach, and we actually reached this conclusion in, and I should say that I'm working with spherical polar coordinates in the Newtonian case. One of the first conclusions you can reach, which we actually illustrate to Physics 1 students, so you have no excuse, is that the torque on an object due to a central force, okay, where R, of course, is the position vector describing the location of the object, but that position vector is anti-aligned with the, or it's aligned, it's co-aligned. It could be pointing with or against the R vector. It's typically anti-aligned. But anyway, because the R vector and the force vectors are along the same direction, then this is automatically what?
0.
0, good. Because the cross product of two vectors which lie in the same direction is 0. But the torque describes the time rate of change of what dynamical quantity? Angular momentum, exactly. So this is actually telling us how angular momentum varies with time. Okay, that is at the level of Physics 1. Okay? So from this we can conclude that L is constant. And now we're going to go beyond Physics 1. Okay? So when L is constant, first of all, L is a vector. And that means that the direction of the vector is constant. But if you think about it, if the direction of the angular momentum vector is constant, then that means that all of the motion of the object in question must lie in a plane. And the angular momentum is then perpendicular to that plane. Okay? So this immediately tells us that we can take any central force problem and we can reduce it to a planar problem, that is a 2D problem. We don't really need to do a three-dimensional analysis. We can do a 2D analysis. So what we're going to do, because we're free to pick our coordinates, we're going to choose our motion to lie in the plane identified by theta equals pi over 2. So that's the polar angle. It usually goes from 0 to pi. And we're just going to pick it so that all of our motion is happening in the pi over 2 plane. It'll just simplify expressions, and we don't really lose any generality from it. It's just, we have a dynamical system, we see everything's happening in a plane, and then we define our spherical coordinates so that that plane is aligned with pi over 2. Which of course means that we're left with a description in terms of r and phi. So theta will disappear from the description because it's a fixed quantity. Now we also know that it's a vector, so in addition to its magnitude, in addition to its direction, the magnitude is constant. And the magnitude of this we can write as the mass of the object in question times r squared times phi dot. Okay, that would be more complicated, except we have set the plane to theta equals pi over 2, so the only angular position we worry about now is phi. So the angular momentum magnitude simplifies. And this is, of course, constant. And one of the things that we can do with this is later on, when it's convenient, we can replace phi dot with the magnitude of angular momentum divided by the mass times r squared. Okay, that's just an algebraic rearrangement of this. Everybody okay with that being the magnitude of angular momentum? Okay, if you've never worked with dynamics or kinematics in spherical polar coordinates, some of this might be a little unfamiliar. That's something you definitely get comfortable with at IMEC. Some of these ideas you might have seen in as early as E&M, I'm not sure, yes?
Are we always going to assume things are plane particles?
So, so sorry. So we are going to be, okay, yeah, so good point. So remember, we're taking the geometry as given. So the big thing, like the planet or the star that's creating the geometry, that's fixed and its effect is encoded here. What we're studying are the little things moving in this geometry. So yes, we're going to approximate them as point particles. Okay? And that's a good approximation if this is a satellite in orbit around the Earth or if it's the Earth in orbit around the Sun. Okay, either one works. But yeah, so I'm doing an analysis of small objects moving in the central force created by presumably some bigger object, which is not moving itself. Okay. So, all right, so as per physics 1, we always have to choose our choice of system. And if I choose my system to be the large mass that's creating the force and the test mass, which I'll indicate by little m, this will be big M, little m, okay? Then what do we know about the total energy of that system? Don't make me draw a card. There, I drew a card. Avery!
I can't see the board.
You can't see the board for reals? Is it too dark?
No, I don't have my glasses.
You don't wear glasses.
No, that's
You do, okay, all right. So I have two objects in the universe. They're both part of my system. What can you tell me about the energy of that system?
Wait, say that.
There are two objects in the universe.
Yeah,
I choose a system so that both of those objects are part of the system.
yeah.
What external forces are there to do work on that system?
None.
So what is the total energy of that system?
0. It's constant.
Constant. Yeah, it doesn't change. Okay, all right, good. Glad we got there, even without being able to see. So we can, of course, write the energy of this system. And I have MT in a lot of places, and I'm just going to write M, and hopefully I don't get confused. So this is the mass of the test mass. This is capital M, like sharp, jaggy, like you wouldn't want to grab it if somebody threw it spinning at you because it cut your skin M. And this is nice and smooth, like you want to pet it. All right, so the kinetic energy. The kinetic energy is, of course, 1/2 mv squared. Get your minds out of the gutter. You guys are disgusting. The kinetic energy, here, I'll actually go right into detail. So this is V dot V. That's 1/2 mv squared, plus the potential associated with this central force. I'm just going to call that V of R. It only depends on R. And this, by Avery's brilliant insight, due to lack of sight, is that this is a constant in polar coordinates now. And notice we're really working in just polar coordinates, not spherical polar coordinates anymore because we've lost theta. We fixed it, so now we're just working with R and phi. Does anybody know what kinetic energy looks like in polar coordinates?
Yeah, 1/2 ion is still.
That's for an object which is rotating. Okay, that's fine. This is not something I'm going to discuss with Dr. Kellen. I'm just going to write it, and you're going to go, oh yeah, I remember that.
Oh, yeah, I remember that.
Yeah, okay, there you go. Okay, hey, shh, my turn. All right, here we go. Important non-intuitive step in the analysis of central force motion is the following. We've got dr dt, dot is of course time derivative. We've got d phi dt. We've got r's, okay? I would really like to reduce this to a one-dimensional equation. That is an equation, a differential equation that is only an equation in one variable. How are you going to do it?
Take your phi dot you solved for over there and plug it in.
Exactly, because L is a constant. So this takes the phi dot and replaces it with a 1 over r squared, basically. Okay? So if we do that, we have in the end the mr squared, this is squared, I'm going to get myself confused. L squared over 2 mr squared. Is that right? Yeah, I can do this. I never trust myself to copy down or to figure out what's got to go from step to step. Anyway, all right. And now what I'm going to do is I'm going to give this thing a new name. Because if you notice, everything here is just a function of r. There's no more time derivatives. The only time derivative of r sits here. So as a one-dimensional dynamical system, this is your kinetic term, and this whole thing is the potential for r. So I'm just going to call this combination the effective potential for r. The important thing to note is that the actual form of this depends on the potential, the fundamental potential you start with, but also the value of angular momentum you're dealing with. And we're going to see how that changes to different results in just a moment. Okay, so this is a differential equation for r as a function of t. Okay. And what I'm going to do now and henceforth is I'm going to say for m not equal to 0, m is equal to 1, which, like, this would probably bother a mathematician if I wrote it. But all I'm saying is, in the situation where the mass is non-zero, I'm just going to set the mass to 1, the unit mass, because I don't want to carry around factors of mass more than I need to. Okay. Of course, if the mass is 0, the value of the mass is 0. All right? Okay, so you can solve this differential equation and figure out the radial motion as a function of time for an object in this central potential. Who wants to do it? Draw a name. Ryan. Is Ryan here?
No.
Went to London.
Chase him. Hey man, can you tell me the solution to that differential equation? Would you like to tell me why that's an unfair question?
Well, you're squaring the derivative. That makes it tricky and not linear.
Why is it unfair to ask someone to solve this differential equation? Say it again?
You don't know what V is.
You don't know what V of R is.
Oh, yeah.
V of R could be, kr cubed, kr squared, like that. I haven't given you what V of R is. It is generally very, very difficult to solve a differential equation where you don't actually know the differential equation. The only case where I know where you can do it is on a non-commutative geometry where you construct non-commutative solid lines and use a projection operator to actually decompose the solutions, but we're not going to do that today. So,
Relaxing words.
anyway. Okay, so no, seriously. So what we're going to do is actually, we're not going to solve the differential equation at all. We're actually going to do something we taught Physics 1 students to do. Okay? We have a completely isolated system with one force. You can solve the differential equations to get an idea of what's going on, but there's also something else very powerful and intuitive you can do. What is it, Gage? Adria?
You just do like the sum of the forces is equal to 0. Or,
Test different values and see what happens if.
No, you guys are too fixated on the equation.
We do the change in E is 0?
You guys are too fixated. Well, that's part of the story, but you're too fixated on the equation. What is it in Physics 1, we give students a system like this, one object moving in some potential energy function, and then we say, you can solve the difference, you can solve Newton's law, but that's going to be really hard. Instead, you can do this, and then you can just read off the answer of how it's going to behave. Graph it, yeah, we'll plot it. Let's just graph what the effective potential looks like. Because that's the power of it. You graph this thing, you end up getting a curve, and then you go, oh yeah, I just think of like a ball rolling on a hill. That's the intuition, okay? So we're going to need an actual form of V of R, and so we're going to use the Newtonian gravitational V of R. So without any further ado, let me see if I can find a place to do this. I'll do it over here. Okay, so if I plot V effective which is L squared over 2r squared, because I've set n equal to 1, plus the Newtonian gravitational potential, which is minus g big, sharp, pointy m, what would cut your skin if you caught it as it was spinning like a ninja star across the room. This is the Newtonian gravitational potential. That mass is the big thing that's creating the gravitational potential. Then we can plot that effective potential as a function of r, okay? And then based on the shape of the potential, we can kind of infer some of the behavior that we would expect, okay? Now the tricky thing here is, as I said before, you have to put in a value of L. You have to say, well, what is the total angular momentum, which is constant, but you have to specify the value. Because, for example, if I say L is equal to 0, we expect different behavior than if I say L is a really big number, okay? So what I'm going to do is I'm just going to plot 3 representative values, L equals 1, L equals 2, L equals 3, and then we'll explore their behavior. So here we go. Let's see if I can do this. So L equals 1, something like this. L equals 2, something like this. And then L equals 3 might look something like this. Okay, so now to really give an interpretation to what this picture is telling us, and these all run off to really give an interpretation of what this is telling us, what we want to do is we want to say, okay, I'm going to put a particle into this central potential, this gravitational potential, with a certain amount of energy. So I can give it some fixed value of energy, say E total, or say E total. And then depending on how much angular momentum I've given it, and remember, if we're giving something an amount of energy, we're talking about, total energy, so it's the sum of the kinetic and the potential. But you still have the freedom to identify how much angular momentum you give it. Because remember, I can take something and launch it with a certain kinetic energy straight at the gravitating object, and that will have a fixed amount of energy. But if I launch it from up here in that direction, it might have the same amount of energy, but it would have a different angular momentum. Because here the angular momentum would be 0 because it's going straight toward the center, but here it's off-center, so it would have some non-zero angular momentum. So the angular momentum and the total energy are somewhat independent, okay? Somewhat independent. Extreme cases, they can determine each other. Okay, so let's talk a little bit about what happens if our total energy is in this case. So here we have a situation where if we draw our energy bar from physics 1, it intersects the L equals 1 curve at that point. And remember, one of the fundamental rules of using potential energy curves to analyze the motion of things is that you can never do what? So what's the advantage of drawing this energy bar? What does it kind of tell you? You can't go higher than the energy bar, because that would somehow be getting more energy than you gave the system. But that means that your motion is restricted to this part of the effective potential curve. Okay? Now what does that motion describe? What that motion is actually describing is situations where you're sending the object in with some non-zero angular momentum, but the object is coming in from infinity, coming to a minimum closeness, and then going back out to infinity. That's a scattering situation. Something comes in from infinity, it gets near this planet, it kind of curves a little bit, and then it goes off to infinity. Right? Good? Okay, now let's take this energy. This energy gets 2 interpretations. First of all, if you happen to send it in with the L equals 2 amount of angular momentum, This thing is actually stuck right there. What kind of motion is that describing?
Circular.
That's a circular orbit. You're fixed at a constant value of r. So in this situation, you're undergoing a circular orbit. Okay? What if I take this and I am actually giving the object the L equals 1 angular momentum?
Elliptical.
Say it again?
Elliptical orbit.
That's an elliptical orbit. Okay? You're bound between these two radii, and you just oscillate back and forth between them. Now, this is just the radial part of the motion. You also have an angular part of your motion because you have non-zero angular momentum. So you're going around the thing, that's just captured by this angular motion which we've wrapped into L. So in this situation, we have an elliptical orbit. And as usual, the large gravitating object is at the focus of the elliptical orbit. Okay? Now, last but not least, these orbits, the circular orbit, the elliptical orbit, these, yes?
So how would we interpret that lower energy in terms of L equals 3 since it can never even...
You can't. Like you literally, to give something L equals 3, you have to give it more energy than that. That's how you would interpret the fact that this curve, or that this line never crosses that curve. But if you think about it, this should make sense. Like if you want something to actually be in orbit, you can't give it too much energy. Because if you fire it in with a hell of a lot of energy, it's not going to be gravitationally captured. It's just going to scatter. Okay? Okay, so two comments before we move on. First comment is that both the elliptical and the circular orbits are stable. And what I mean by that is if I put something in a circular orbit, and then I come in and I thump it, maybe give it a little bit more energy, all that that's going to do is bump it up here, and it's going to turn into an elliptical orbit. Okay? Approximately the shape of the circular orbit that you perturbed. Similarly, if it's in the L equals 1 case and you're doing an elliptical orbit and you give it a little bit more energy, it's still going to be in an elliptical orbit. It's not like you're going to thump it a little bit and all of a sudden it's going to fly off to infinity. Okay? All right. The second comment I want to make is that in this analysis, everything was assuming that n is greater than 0. That is, we're assuming that the object that's moving around this gravitating source has a positive mass. What does the story look like if the mass of the object is 0? What kind of trajectories do we get? Remember, this is Newtonian gravity. Yeah, we get straight lines, exactly. We get undeflected paths. You could just shoot it straight towards the thing, let it collide if you want, but you can't get an orbit. That's the point. Okay, massless things are always going to undergo this sort of trivial dynamics. Okay? Questions? Okay, and you can actually get this mathematically out of this expression just by taking this term to 0. Because if the true potential V of r for a massless particle is 0, you still have an effective potential because this thing has angular momentum. And so this L over mr squared is non-zero. So when you analyze it in spherical polar coordinates, you can still get the effective potential part to this story, but the true underlying potential is 0. So if you construct the associated curves, you'll find that if you translate it back to a flat version of the motion, that you always just get these straight line trajectories. Okay, we good? We cool? Cool, good. All right. So now it is time to do this in GR, in the Schwarzschild geometry. I taught this class, maybe it was the last time I taught it, and I called this the Schwarzschild metric. And then some dude left a comment, it's like, you should put a nonsense Schwarzschild.
And you listened?
Now I can't even spell the damn thing because I want to phonetically spell it. Schwarzschild. All right. So we've got our metric for the Schwarzschild videometry. All right. And one of the important things to notice about this metric, which is probably obvious, but I just want to remind you. The inverse metric is not the same. Okay? It's diagonal, so the inverse metric is easy, but it is definitely different. And so you have to be very careful when you're writing down explicit expressions. Am I supposed to use the metric or the inverse metric in this particular place? Okay, so what we would like to do is an analysis similar to what we did for the Newtonian case. But we got to be a little bit careful because, like, how do we even start by writing down an energy expression? Like, do we still write down 1/2 mv squared? Does it look the same? What are these coordinates? What about the geometry? Like, how does that all play into the story? Okay. Well, what is valuable about energy as a tool for calculating things in Newtonian mechanics? Like, what's so valuable about it?
It's math easier because you don't only have to consider the input.
Well, that's true. You can use the work energy theorem, but in practice, how do we usually use the work energy theorem?
We say it's constant.
Right, we take the system to be everything, and therefore the total energy is constant. Alternatively, the work energy theorem is a statement about the conservation of energy. Okay? So our Newtonian analysis was really kind of built on the idea of conserved quantities. Do we know how to handle conserved quantities in GR? Whose equation? Keeling's equation. That's why we studied Keeling's equation. We talked about symmetries and how those lead to conserved quantities. Okay? Everything feeds into everything. Okay, so the first thing to note is that our metric is independent of which two coordinates? Sure.
Time and feet.
Feet, right. There's r and there's theta in there, but there's no t in feet. Okay? So g mu nu is only a function of r and theta. So what that means is that we can immediately write down two killing vectors. One killing vector for the fact that you can change t and the metric doesn't change, the geometry doesn't care. And another killing vector to reflect the fact that you can change phi and the metric doesn't care. Okay? These are the simple isometries of this space that you can get just by looking at the metric and saying, oh, it doesn't depend on t, therefore I can shift t all I want and the metric doesn't change. Okay, the good thing is that since we're working in coordinates tr, theta, phi, the components of these vectors are very simple. For the killing vector associated with the fact that you can change t, it's literally just 1, 0, 0, 0. And for the killing vector associated with the fact that you can change phi, it's just 0, 0, 0, 1. You do not have to take my word for it. You can take this metric, find the Christoffel symbols, write down Killing's equation. Okay, if you don't remember, that's Killing's equation. To solve this, you actually solve for the dual vectors, but then you can find the vectors. But you solve for Killing, you can solve for Killing's equation, and these will be two of your solutions. Okay? But we don't need to solve Killing's equation because we can do the cheat and just say the metric doesn't depend on t and phi, therefore. Now, What we need to get from these, though, is, so what do we, well, let me ask you this. And this is going to be mean, so I'm going to pick somebody I really don't like. People I like so much. You're wondering right now, did he flip my card out on speaker? Does he hate me? Okay, I like everybody, so this is going to be pretty hard. I can't do that. I set that up. That was like too fierce. Okay, anyway. All right. Whose name could I possibly call out after that? Because that's terrible. I hate you. Anyway,
Yeah,
all right. I can tell you who I paused the longest on. No, no. So let me remind you. I hope this is like stirring coals in the memory of the fire of the discussion of killing vectors. You're going to get a homework assignment over that, or at least a question or two. But just remember, the way that we take killing vectors and get conserved quantities is we say, if I take a dual killing vector and I contract it with a generic 4 momentum, then this thing gives me what I call the conserved component of the 4 momentum. Okay? So this is how we get from killing vectors to conserved quantities, conserved components of the 4 momentum. Now, the immediate thing you see is that if I have the killing vectors, I need to first form their duals. But the duals are not trivial, because to get the dual of this, I have to apply the metric to it. But the metric has these funky factors. Okay? So, without any further ado, if I dualize this guy, then I'm going to get now a vector minus 1 minus 2 gm over r, 0, 0, 0. And if I dualize that guy, and I guess this should be phi mu, and this should be t mu. I don't know why I would ever change this. Anyway, if I dualize this guy, then I'm going to be using this factor in the metric. And so my dual killing vector is going to be 0, 0, 0, r squared sine squared theta. Okay. And now I can find the conserved momenta by taking k t mu and contracting it with p mu, and k phi mu and contracting it with p mu. Okay. Now remember, how do we define p mu?
Gamma and gamma b.
Well, those are the components, but how do we define it in total?
Times 4 velocity.
Say it again?
Times 4 velocity.
Yeah, it's the mass times the 4 velocity. Where the 4 velocity is dx mu d lambda, where d lambda is some parameterization of the path. Okay? So I'm setting m to 1, again, whenever m is not 0. So this is just going to become k t mu dx mu d lambda, and k phi mu dx mu d lambda. Okay? And now we can do that, okay? Kt mu only has a non-zero component here, but that's when mu is equal to 0. That's the time piece. And that means I'm going to have dt d lambda here. Okay, so I have minus 1 minus 2 gm over r dt d lambda. And that's the only thing I get from that one. And then similarly, when I do this guy, this is only non-zero in the last term, and that's the phi term, and so that's going to come in with d phi d lambda. This is going to be d phi d lambda. And so here I'm going to get r squared sine squared theta d phi d lambda. And these are constant quantities. Okay? And I might as well go ahead and identify these for what they are. The conserved quantity associated with time translation invariance is what we call the energy of the system, and the conserved momentum associated with the phi translation invariance. And I say phi translation in the sense that I am taking the value of phi and translating it along the phi axis. You think of it as a rotation, and that's fine. That's the angular momentum associated with the phi rotation plane. Now, I got dt d lambda, I got d phi d lambda. I ain't got dr d anything. And you remember in the Newtonian case, we were working with a differential equation for r. Because ultimately, we reduced this to a one-dimensional problem in the radial position. So I would like to somehow, out of this analysis, get a differential equation for r that I can maybe plot and then compare to the Newtonian case. So to get a differential equation for r, we have to actually work a little bit harder. So there is yet another conserved quantity we can consider, and that is minus g mu nu dx mu lambda. Okay. To prove that this is conserved, let me very quickly calculate its directional covariant derivative along the path lambda. I moved the derivative of epsilon past the g mu nu because we defined our derivative to be metric compatible. We can move it past the derivative and not worry. Even if the metric depends on coordinates. Okay. The fact that the fact that the metric is covariantly constant was one of the conditions we used to derive the form of this derivative. So then I'm just applying the product rule to these two terms. But these, for geodesic paths, which is the kind of motion that we're considering, it's the motion of things in the presence of a gravitational field, these two quantities are just the geodesic equation. So these are both 0. That's the geodesic equation, that those terms are equal to 0. So that means that this quantity epsilon is covariantly constant along these paths. Yeah.
What is epsilon?
I'm about to tell you. Okay? So, well, actually, no, I'm not about to tell you. I lied about that.
Okay.
Okay. So, well, in one case, so one interpretation of epsilon, if you remember, we actually calculated this for massive particles. And for massive particles, we took the parameter lambda to be the actual length of the path. We called that proper time, but we used the length of the path for the parameterization. And this quantity just came out to be -1, which is clearly constant. Okay? We're not restricting ourselves to massive particles at this point because I want an analysis that I can apply to massless particles as well. But what's good is that we can take this expression and we can now combine it with these conserved quantities to beat something that has d something out of it. Okay? So let's actually write down this expression explicitly. So minus g mu nu dx mu dx. So this is a diagonal metric. So the only non-zero terms are the g00, or you would call that the gtt, the grr, the g theta theta, the g phi phi. So that's going to be dr d lambda, dr d lambda, dt d lambda, dt d lambda, you know how it's going to go. So I'll just fill in what we get. So for the time terms, for the RR terms, for the phi term, okay, and in this, and so let me make one more. Let me make one more observation up here, which I forgot from my notes. So the fact that we have this killing vector here associated with angular momentum being constant means that once again we can reduce this to a two-dimensional process. If you have any component of angular momentum constant, that means that in 3 dimensions everything's happening in a plane. So we can take this and we can go and set theta equals 2 pi over 2 again. So this is just going to be 0, 0, 0 r squared, and then down here, this sine squared theta is going to disappear. And then when I consider the d theta, d lambda term, that's 0 because theta is not changing. We're stuck in the theta equals pi over 2 plane. Okay, so these are the only 3 terms I'm going to have in this quantity epsilon. Hey, this is looking good. You guys see what I see?
Math?
Math. No, look. dt d lambda is related to a constant e with this junk, and that's what appears there. d phi d lambda is related to a constant L divided by r squared, and that's what appears there. And then we're left with dr d lambda. Holla! I know. Okay, so we can take this expression and we can beat it into the following more useful form. E squared over 1 minus 2gm over r minus drd lambda squared over 1 minus 2gm r, 2gm over r, minus L squared over R squared. Okay? Simplifies nicely. Very nice.
That's nice.
That's a question? Is that nice?
Doesn't look nice.
Is that nice?
It's not that bad. Okay, so what I'm going to do now is the following, and because I'm going to erase all this work because I've got to have room to draw my pretty pictures. So what I'm going to do with this is, in analogy to what I did in the Newtonian case, I'm going to solve this for the energy equals something. Remember in the Newtonian case we had the energy was equal to the kinetic energy plus the potential, and then we did that cool effective potential thing. Okay? I'm going to take this and solve it for energy equals something, and then we're going to use that expression in a manner analogous to what we did with the Newtonian case. Yes? Okay? So let me let me actually just say very quickly before I erase all this because you'll forget. When an object is massive, what is the value of epsilon? -1. It's -1. Okay? Here's where it gets tricky. When an object is massless, what is the value of epsilon? Well, epsilon is this. Folks, this is minus ds squared. What is minus ds squared for a massless particle? So let me just give you the expression for ds squared in Minkowski space where you're used to it. Okay? If you're massless, then that means that your velocity, which is dx squared plus dy squared plus dz squared over dt squared, your velocity squared is equal to 1. Because 1 is the speed of light. But what does that make ds squared? Say it loud, say it proud. It's 0. ds squared equals 0 is the definition of the path of massless objects. But that's how we're defining this epsilon. So for massive objects, epsilon is -1. For massless objects, epsilon is 0. This case depends on you parametrizing the path with proper time, okay, which is what we conventionally do. So that's why this kind of looks like a discrete change. But nonetheless, when I solve this for e squared, this thing, epsilon's going to appear. And then we can look at the massless and the massive case just by taking different values of epsilon. Okay? All right, so coming back up here and making some room. All right, solving this thing for e squared, and I'm just going to throw a factor of 1/2 out front for convention. I have 1/2 dr d lambda squared plus 1/2 epsilon minus gm over r epsilon plus L squared over 2R squared minus GML squared over R cubed. Okay. Where we remember Are you ready? Are you ready?
Yeah!
Nice. Okay. So that was my fun voice. That's like my orange shirt voice. Okay. So for m equals 0, this will be our first case. If m equals 0, this term disappears, and we have these two terms. Huh. For m equals 0 in the Newtonian case, that term disappeared because this comes from the actual Newtonian potential, which doesn't affect massless particles. You still get this term because of the angular momentum, but in general relativity, for massless things, you get the potential term, the effective, the angular momentum term, but you get this term. This is new. This is the difference between general relativity and Newtonian gravity for massless particles, this term. Okay. These are 0 for massless particles. So if we plot this thing, I'll do it this way. What we find is a very interesting result. R equals 2gm clearly plays an important role in this geometry. And we'll explore the relevance of that later. That when R is equal to 2gm, the terms in parentheses are 0, and things are obviously going sideways. But from R equals 2gm, what we find is the following. For different values of L, the effective potential curves look like this. Where that's the L equals 1, 2, and 3 curves. Okay? So now let's use what we talked about to explore motion in these cases. If I give myself a total energy, E total, and an angular momentum that corresponds to 3, then what I find is what kind of trajectory? I find a circular orbit. In fact, for each of these angular momenta, if I give it just the right amount of energy, I get a circular orbit.
Should those peaks necessarily be straight on top of each other?
I don't remember actually. I don't remember. You can generate the curves and figure out whether they line up.
Those are all unstable, right?
They're all unstable.
But they're orbits?
Notice if I made exactly this circular orbit and I perturb it a little bit, it's going to roll down this potential curve. So we find two interesting things. First of all, we find that massless particles can undergo circular orbits. That is clearly different than the Newtonian case. Clearly, gravity is affecting massless things. Moreover, the orbits of those massless things are unstable. So if you could set up one of these orbits, you could just poke it, and its instability would further reflect that this is the correct result. Okay? Now, to be completely honest, it is very difficult to get massless things in orbit. Okay? So we really want to focus on massive things, and for the massive case, we have the following result. if I plot the effective potential as a function of position, then we again find something interesting happening at 2GM. I'm going to draw this value of the total energy being 1/2 as a reference, and then what we find is the following. Okay, we have L equals 1, L equals 2, and L equals 3. Interesting. Interesting. If your angular momentum is too low, you have no chance of having a stable, or you have no chance of having a circular orbit. Okay? Get your angular momentum up high enough, and you eventually develop both the possibility of an unstable circular orbit and a stable circular orbit. Okay? The stable circular orbits are akin to the stable circular orbits of Newtonian. In the Newtonian case, the unstable circular orbits, though, that's a bit new and weird. Okay? Go ahead.
So does that line cross 1/2 again then, if it's stable? It's not an
Well, it doesn't actually matter. I mean, these are all asymptotic to 1/2. If you take r to infinity, E is just going to go to the value 1/2. But this is stable because it's a minimum. Okay? I can poke it away from that minimum value, and it will roll right back. Now, what this means is that as we vary the value of the angular momentum, you can imagine that these curves eventually deform into these curves. I mean, L is a continuous parameter. You can tune up L. But what is happening, at a certain point, the curves are going to get to a place where you form this pair that splits and moves away into the maximum and the minimum. So if I work it backwards, if I lower the value of L, eventually these two things will move together. And then below that, you'll just have curves of this form with no maxima and no minima. Now here's the interesting thing. If I run this backwards, and these two things come together at, say, some situation like this, where these two things are coming together, what that means is that there are no possible stable circular orbits for r less than this. For any r less than this value, the only circular orbits you have are unstable. Okay? Now it is interesting, and you can actually solve for that value, because all you're doing is saying, I want to find when the effective potential vanishes, and this is going to give you the radial position of the unstable and the stable. You're just looking at when the derivative of the effective potential vanishes. Go ahead.
So you're saying that that's where there can be no stable orbits, but if it doesn't have an actual maxima, then can it?
It's not even a circular orbit.
Okay.
It's not even a circular
okay.
orbit. Like, you have to have a maximum or a minimum to have a circular orbit.
Right, yeah. Okay.
And then whether it's a maximum or min determines whether it's stable. So you can take the derivative of the effective, we're in the massive case, so epsilon is 1. Okay. So take this thing, take the derivative, set it equal to 0, solve for r plus and minus, and you're going to find, of course, a lovely quadratic. Okay, where the larger value is the stable one, and the smaller value is the unstable one, as is indicated by the picture. And then all we want to do to figure out this sort of threshold case is find the condition when r plus is equal to r minus. That is, for what value of L does these two things come together at the same value? And you can actually solve for that. That's what we're going to call the critical radius. And the value of the critical radius is L squared over 2gm, which is 6gm. Okay? So a prediction of general relativity is that if you have a star or planet of mass m, you cannot have a satellite in a stable circular orbit at a radius smaller than this. Yeah.
Is that a 12 in the calculator?
Yes, that's a 12. Okay. Well, this is a way to test GR because you can. It's not time yet. Are you really, you can do it? You can leave? I gotta do it.
I'm just zipping up my bag so you know.
You're zipping up your bag. Okay. Well, let me make this little list, and then I'm gonna have to talk about. Oh, shit, you guys, I'm running out of time. I mean, I could do the perihelion shift, or I could not do the perihelion shift.
Yeah, you.
I what?
You're fine.
I'm fine. Okay, but I think I might be a little bit dirty. It's gonna get a little bit filthy. We'll talk about perihelion shift. Because somebody's got to run, because somebody's got a train to catch. Okay, all right. Yeah, let me make this list, and then I'll take my clothes off, and we'll do the perihelion. Okay, so let's ask ourselves. Let's ask ourselves if this affords us a true test of general relativity. So if I make a quick list of a couple of astronomically significant things, for each of them, I'm going to calculate the value of 6 times g times the mass of the quantity in question. So for the Earth, it's this. If you want to actually track the numbers, this formula secretly comes with a factor of 1 over c squared. You need that in order to get the right units. But if you take this, c is a universal constant, 6 is certainly a universal constant, g is gravitational constant, that's Newton's gravitational constant. You plug in the mass of the Earth, and you find that the critical radius is a whopping 0.03 meters. Okay? Now, given the fact that the radius of the Earth is 6 times 10 to the 6 meters, that means that in order to test this, you would have to have something in orbit inside of the Earth.
Seems to make sense.
Which you can't do. Like, that's hard.
Can things inside?
Gabrielle, it was funny because Gabrielle was like, oh yeah, but you do the hypertunnel thing and then you just put it in orbit inside the Earth. I'm like, but Gabrielle, it's only the mass inside that matters, and so the quantity here would decrease. He's like, oh damn. Maybe the sun. Maybe the sun. So this is so in this case, RC is inside of the Earth. That is no good. Okay, the sun is obviously gooder because it's got a bigger mass. That's going to make this distance bigger, and in fact, it turns out to be 8,850 meters. I know, that's really, really big. Except for the fact that the sun's radius is about 7 times 10 to the 8 meters. So again, we find that the critical radius in which we have to do this is now inside of the sun. Good luck doing that experiment. Okay, there are more extreme astrophysical objects. If we have a white dwarf, we'll talk about what those are later. If it's a solar mass white dwarf, so it's got the same mass as, say, our sun, then this quantity is going to turn out to be the same, because it just depends on the mass. But the size of a white dwarf, which is pretty small, turns out to be on the order of 10 to the 6 meters. Crap. Smaller things exist. Neutron stars exist. For a neutron star that's basically the size of the sun, this is again 8850. And for a neutron star, the radius is a whopping 10 to the 4th meters. Again, we're screwed.
Is that even possible? Don't neutron stars have to be like 1.7?
Right, and that's not going to help the situation. That's only going to make it worse. Okay? The only thing that saves us in this story is a black hole. Of course, black holes have to be larger mass than the sun, but let's just say we had a solar mass black hole. In that case, again, the critical radius below which you cannot get circular orbits is 8850, but the radius of a black hole is 0. It's a singularity. You might say, oh, well, you got to be outside the horizon of a black hole in order for this to even make sense, and I agree with you. The problem, though, is that the horizon of a black hole is at 2 GM. And this is outside of it. So if you had a black hole and you could test orbits around it, you could actually use this as a test of general relativity. Okay? However, we have not got that close to black holes, so we're not going to be able to do it. So I am going to talk about a real test of general relativity, because I want to leave you with confidence that this is actually true. But it's getting awfully hot in here.
So take off all your clothes.
It's only getting hotter. Only getting hotter.
Well, take out your Snapchat.
And so, at this point, in my awesome shirt, which you should all be jealous of, I'm going to very quickly as I can, go to the perihelion shift. Unless anyone has anything that they would like to contribute to the discussion.
I think a couple people do.
Okay. Well, I'll erase the board while you bring your contributions forward.
Start.
Oh, no.
I gave $3.
Do you want to do it one at a time?
Each sandwich.
I know you're a lot more sticky.
Just
Just go for it. She's just eating the dog. She's eating.
okay.
You want to do it at the same time or
No.
Just remember, this can hurt.
Yeah,
so
Yeah, no, I'm going to do it.
Be a little
I'm going to do it.
Give us a 3, 2, oh, you didn't give us any warning.
Does that okay? Did that hurt?
Very good. It's a good look. I need a new hair product. I need a new hair product. So I'm thinking of apple pie.
How do you do that? So what do we do with it?
Is that safe, Caleb?
Yeah, it's,
Okay.
I'm sorry.
All right.
You're gonna stop it.
Really though, what do we do?
Just throw it in the trash?
I don't think you want to eat it after it's been on my nasty face.
Do you want to eat it?
No, I don't. Okay. Thank you for your contributions to class today. They were tasty. Okay. You guys were great. Like, that was literally the most gentle pie I've ever had.
Yeah, if I would have done that, it would have been.
So the worst, for those of you that haven't heard the story, the worst I ever had was Joe, God, I can't remember Joe's name. It was a whipped cream pie, and I decided I would let him run and pie me. And he ran from like 30 feet away and held the pie out and never slowed down. And in addition to just the pain of being slapped at full throttle, the whipped cream went into my brain. I had the smell of sweet nastiness in my head for like days.
Have a good spring break.
See you later, you too. Okay, back to the real deal now. All right, so I'm going to do this as quickly as I can because it's the real thing. All right, so the perihelion, if you've never heard of this being defined for you, we have, in typical orbital scenarios of planets around the sun, they follow elliptical orbits with the sun at the focus. Cherry up my nose, but it's all right. Okay, so the point of closest approach, this guy right here is called the perihelion. Okay, it is the position in the orbital path of an object of closest approach to the source of the gravitational potential for the orbital path. Okay, so I'm going to just write down the results. In the Newtonian case, where again the energy can be written in the following form. The question is, should I clean my face before I go to dinner with my family?
I don't advise it.
Yeah.
I'm sure your parents will love it.
Okay, so that was our expression for E. This is the effective potential. But then what I'm going to do is I'm going to use the fact that this is constant to replace the time derivative where it appears here for a phi derivative. Okay, I can solve this for dt equals d phi with a bunch of crap, and I can turn this time derivative into a phi derivative using that expression. In particular, dt is r squared d phi over L. And then our equation up here is going to become dr d phi squared, and I'm just going to move it around a little bit, minus 2gm over L squared, r cubed, plus r squared, and that's going to be equal to 2e over L squared r to the fourth. Okay. Now the important thing in looking at this equation is, first of all, the g's are constants, the m are constants, L is a constant, E is a constant. They're all constants. The function that you're trying to find here is r is a function of phi. That is, how does r's position change as the angular position changes? Before we were talking about r as a function of t, but what we want to do now is analyze the orbit itself, and we want to ask, how far away from the sun are you as you change your angular position? So we're really after r as a function of phi. And it turns out that you can solve this equation. We are certainly not going to solve it, but I'm rather just going to write down the solution. The solution is L squared over capital G times n times 1 plus E cosine phi, where this quantity E is itself a function of G, M, and L. So E is a constant because G, M, and L are all constants. Okay? This is sort of the most concise form to put it in. And what's useful about that solution is that it immediately tells us that if I take the value of phi and I increase it by 2 pi, that I end up right back at the value of r that I started at. Okay? How can we see that if I start at a certain distance for phi equals anything, you could say phi equals 0, and I go all the way around once, I end up at the same radial position? How can you see that from that solution?
Because the only phi dependence is in cosine.
Exactly, because the only phi dependence is in cosine, and cosine is periodic in 2 pi. Okay. Yeah, the cosine is sitting in here in a weird way, but the phi itself sits by itself in cosine. So when phi is increased by 2 pi, you're going to get back to the exact same value of the function. Okay? Now in GR, the answer is going to be different. In GR, and I'm just going to give you the answer, using the effective radial potential that we derived earlier, okay, and then playing out the same story, we're obviously going to get a different solution because we have a slightly different effective potential. We had that extra GR term that I pointed to earlier. And in this situation, our r as a function of phi comes out to be L squared over gm 1 plus E cosine of 1 minus alpha of phi. Where this quantity alpha, and again, this would come from actually solving the differential equation, is equal to 3g squared m squared over L squared. Okay, so what's the first thing that you notice? Is it still periodic in phi?
Yes.
So if I start out at, say, phi equals 0, when the cosine term here is 1, I'll get some value of r. And I think I said where, so cosine of 0 is just 1. But if I, instead of 0, consider 0 plus 2 pi,
It's not periodic in 2 pi, but it's periodic. So, 2 pi over.
yeah, it's no longer periodic in 2 pi, but it's periodic in, I heard somebody say it,
2 pi over alpha.
2 pi over 1 minus alpha, okay? So it's periodic in 2 pi over 1 minus alpha. That is, if I increase phi by this amount, then I come back to the same radial position. Okay? Now let me explain to you what that means. Let's take the perihelion as the radial position we want to start with. That's the closest approach to the sun. What that expression is telling me is that if I go around the circle by 2 pi, or sorry, what it's telling me is to get back to that same distance, I do not want to go all the way around the circle by 2 pi. I want to go around the circle by 2 pi over 1 minus alpha. Okay. Now, for small alpha, this is just 2 pi times 1 plus alpha. And so the periodicity we can think of as being shifted by an amount 2 pi alpha. So for every trip around the sun, the position of the point of closest approach moves by an angle 2 pi alpha, where alpha is given by that combination of things. Okay? So, first and foremost, clearly in distinction to the Newtonian case. The Newtonian case would predict that the perihelion doesn't shift at all. So if you see any shift, then you know the Newtonian limit doesn't work. But you actually get quantitative agreement. So let's see what how the quantitative agreement works out. So first of all, the thing we have to calculate is what is delta phi? Oh, God. And that's 6g squared, and this is just using these results, 6g squared m squared pi over L squared. That's easy to calculate. You know 6, you know g, you know m, you know pi. M is the mass of the sun. But what do you put in for L? Like, what is the value of the angular momentum of something orbiting the sun? What is L? Well, to get L, we actually have to consider the geometry of the orbit of it. Because we know about ellipses. So if you ever wondered when your 7th grade conic sections unit in algebra pre-calculus was going to come in handy, now is the time. So the equation of an ellipse as a function of phi can be written as 1 minus e squared a over 1 plus e cosine phi, where for our ellipse, what we have in mind, so every ellipse has 2 foci, we're parametrizing the position by an angle phi like so. And from the center of the ellipse out to one of the far edges is the semi-major axis. And from the center of the ellipse up to one of the closest edges is the semi-minor axis. So A is the semi-major, B is the semi-minor. And then the eccentricity of the ellipse is the square root of 1 minus b squared over a squared. Okay? The eccentricity is basically measuring how far deformed from a circle it is. Because if this was a circle, what would be over AB? It'd be 1. If it was a circle, the B over A, B and A would be the same, so the eccentricity would be 0. Okay, Caleb, I knew what you were talking about when you held up the goose egg. Okay? Now, if we compare this formula to the Newtonian result for r as a function of phi, which I just conveniently erased, that result was L squared over GM 1 plus E cosine phi. And now watch. This is a geometric equation. Everything in this equation is from the geometry of the ellipse. You can, in principle, I wouldn't be that good at it, but you can watch planets in their orbits and discern the geometry of the ellipse. But then comparing it to this equation, it tells us that L squared over GM must just be 1 minus E squared times A. Or L is the square root of GM times 1 minus E squared A. So I can figure out the angular momentum of a planet in orbit in terms of constants I know and the eccentricity and semi-major axis of the orbit. Okay? So you don't go out and have an angular momentum meter and hold it up to the planet and say, what's your angular momentum? You measure quantities that you can observe from afar, the geometry, and that gives us the value of L. And then at the end of the day, using that value of L in this expression with all of these other parameters, this comes out to be 6 pi GM over 1 minus E squared A. And one of the things that you notice is that the effect is going to be largest when A is smallest. That is, when the semi-major axis of the ellipse is the smallest it can be. Surveying the, how many are there now planets in our solar system? I forget. 8? I think the last time I gave this lecture there were 9. Surveying the planets in our solar system, who has the smallest value of A? Mercury. So if you're ever wondering why it was the perihelion shift of Mercury that they used to confirm GR, it's because Mercury has the smallest semi-major axis. It gives you the largest effect. Okay? So, what does this effect end up being? Well, for Mercury, this, of course, is the mass of the sun. That's the thing that's causing the orbit of Mercury. We can plug in the geometric information we know about its orbital path. We can plug in the eccentricity. We can plug in the value of A. We can plug in the mass of the sun. If you're curious what those values are, A is 5.79 times 10 to the 10 meters. The eccentricity turns out to be 0.2056. And the period is 88 days. And what we can do with this, so we can use these parameters to figure out the shift per orbit. But then if we know the period of the orbit, we can figure out a more reasonable number, which is the perihelion shift per century. Because this is an incredibly small number. You have to compound the effects over a very large time interval to build up an actual observable effect. A century, we do have, astronomical data that's very old. And so what we want to compare to is the calculation of this over a century gives us that Mercury's perihelion should shift by delta phi is 43 seconds of arc per century. Okay?
Is that a century for Mercury or a century for us?
That's a century in the time of everything. So a century, yeah. So it's the second that we're using.
Okay.
Yeah. Okay. So then, of course, so we've done a calculation. We did a calculation here. We did a calculation using observed values of E and A, but we didn't observe the perihelion shift. We just looked at the geometry of the orbit. So now we say, okay, now we go and we look at the perihelion over time, and we see how much it shifts in a century. Okay? And presumably, if the number matches GR, you're good to go. All right? So this is predicted. Observed. Are you tense? You ready? The observed value of the perihelion shift of Mercury is 5,601 arc seconds per century.
Huh.
We did it.
Okay. However, in all of our analysis, we've been making lots of simplifications. For example, we assumed the sun was a sphere, that it has no angular momentum that would make it oblate. Okay? We've completely ignored the gravitational pull from the other planets on the planet Mercury. Remember, there are other sizable planets that can influence Mercury's orbit. If you actually take into account all of the known corrections to Mercury's orbit that you can get from a Newtonian analysis, the known corrections to the Newtonian result is delta phi being 5,558 arc seconds. So before general relativity, using the Newtonian analysis, they had gotten a mismatch with agreement of exactly 43 arc seconds.
And so that's.
And so when general relativity came along and said, actually, the answer that you get should be supplemented by an additional 43 seconds of arc, that was the first experimental confirmation of general relativity.
Wait, so those are the known corrections using Newtonian mechanics?
Yes.
Okay.
And you can take these corrections and further utilize GR to refine them, but those effects are incredibly small. Okay? I mean, the leading order effect is always going to be the dominant contribution from the sun pulling on, the sun as a sphere pulling on Mercury. And anything outside of that particularly simple scenario is going to be minor, but GR itself is taking that scenario and then turning it into a completely different theory. Okay? All right, so hopefully you are somewhat confident that general relativity is the right way to go. When we come back after spring break, I will not have pie on my face, and we will derive the Schwarzschild solution. That will be fun for those of you who like to solve differential equations. For the rest of you, bring a good book. For Mike, bring toothpicks to keep your eyes open. But we have to do it. It's a necessary evil because I do not feel comfortable telling you about black holes until I have shown you where the hell they're coming from.
Did you make that shirt?
I made that shirt today during the meeting with my ADA officers. I was like, the shirt's probably ruined now, but it'll forever and always be my Pi Day shirt.
There's nothing on it.
Okay, I believe you.